The afternoon session of the workshop. Our speaker for this session is Nadhir Ben Rached, who's currently a researcher in Aachen. He did his PhD here at KAUST and has held researcher positions at Aramco, QMIC, and UNSW, and has research interest in Monte Carlo methods, wireless communications, and rare events. And he will be speaking on rare event simulation techniques with applications in wireless communications. So please take it away. Thank you for coming.
Thank you very much. I would like to thank the organizers for giving me this opportunity. So as Professor Jaffa said, I will talk about rare event simulations with emphasis on applications and communication systems. So my talk is mainly divided into two parts, and I will just start with the first one. So on the first part, we consider the problem of estimating this rare event probability that is given by the left tail of sums of IID random variables. And the particular interest goes to the rare event regime, where n, the number of random variables, is large, and gamma, the threshold, is relatively small. So this has a lot of applications, and here we just emphasize on applications on the performance evaluation of communication systems operating over fading channels. There is other applications, for instance, in finance, where we aim to compute the value of risk of some financial portfolio. So just to motivate why we care about rare event. So for 5G and 6G systems nowadays, it's often we encounter the problem of estimating failure probabilities, like outage probability or outage capacity, that are of order of 10⁻⁹. So this relatively small probability, even if it's small, it has to be estimated accurately and efficiently. So that's a very small example to just motivate the problem. If you consider a transmitter with single antenna that is communicating with the receiver that has multiple antennas. And then, so the receiver is receiving the same signal over this multiple antennas and try to do some signal processing algorithm in order to increase the signal to noise ratio of this simple communication system. So it was shown that for this communication system, the signal to noise ratio is given by this expression here, where the source of randomness is just the fading channel envelope, which we call here Ri. So P and Q are just two integers, and they depend on the way we do the signal processing algorithm to combine these branches. So the outage probability is very practical performance matrix that is used to assess the performance of a communication system. And it is defined as the probability that the signal to noise ratio is less than a given threshold. And if you go back to this expression and try to work out a simple computation, then we get that the outage probability is just the CDF of some fading channels envelope, some random variables. So it is well acknowledged that the use of crude or naive Monte Carlo is very expensive and not efficient in the regime of rare events, and we need to use some variance reduction techniques in order to overcome the failure of Monte Carlo. And in the literature, there are a lot of research effort in these directions. They use, for instance, importance sampling, conditional Monte Carlo, control variator, or a combination of them in order to solve this problem. However, a common feature for this problem, for these estimators, is that the efficiency have been studied for a fixed n, and gamma is relatively small. And we observe that the efficiency of this estimator is considerably affected when n is relatively large. So to convince you, let me start with this motivating example. So we start with the quantity that we would like to estimate. We just write it as the probability of the same event intersect with a larger event somehow. And then we use importance sampling here, where the importance sampling probability density function is just the truncation of the original one over the n-dimensional hypercube. Then what we do, we basically run Monte Carlo here for this importance sampling estimator. So what is proven here is that for a given n, fixed, not large, this estimator behaves very well as gamma is small. And it has what we call the bounded relative error property, which means that the squared coefficient of variation, which is defined as the variance of an estimator over the probability squared, is bounded. And this means that the number of required samples that you need to meet given accuracy requirements remains bounded independently of how small your probability. So this is a very strong property in the field of rare event simulation. But if we try to check the efficiency with respect to n, we just first use the Chernoff bound to just bound this probability by this expression here. And then we compute the squared coefficient of variation of our estimator. And it is given by this expression on the right-hand side here. And by taking eta to be just, for instance, 1, and asymptotically, the squared coefficient of variation is just 1 over the probability, we see that the squared coefficient of variation with respect to n is increasing exponentially. So this log term here actually is negative. That's why we have minus and minus. So it will be increasing exponentially, and this is a very bad behavior. So I would like now to talk about a very known technique of importance sampling that is commonly used in rare event simulation, which is the exponential twisting technique. So when applicable, this technique is known to be to outperform other existing techniques. So it's very useful in practice. For instance, just to motivate this, when we have the light tail distribution, so light tail means that the distribution have a finite normal generator function. This technique here, the exponential twisting technique, was shown to be very efficient for this type of probability, for this right tail probability. For the left tail setting, which is the purpose of this talk, this technique also has been shown to be very efficient for the particular log normal case, which is very challenging in communication systems. Another way to better understand this exponential twisting, so we can easily show that this exponential twisting is the solution of this minimization problem. Basically, if we minimize the Kullback-Leibler distance between function g that we want to find and the original PDF, under the constraint that g is a valid PDF, and the expectation with respect to g of this sum is equal to gamma. So this means that the rare event, which was rare in the underlying distribution, is no more a rare event. It is in the mean of the new distribution. And if we solve this optimization problem, we find the solution here. And theta star that is appearing here is just related to the Lagrangian multiplier, and is called the twisting parameter, is given by the solution of this nonlinear equation. Now, if you go back to this formula here, we can write it as you can see, in the independent case, we can write it as a product of some univariate distributions. And this univariate distribution are what we call the exponential twisting univariate PDF. And the idea is just to take the original PDF, multiply it by this exponential term, and then just normalize by the moment generator function. So for the twisting parameters, in the IID case, this simplifies to this nonlinear equation. So we need to solve this nonlinear equation. It is very important since to remark that since we are considering the left tail region, the exponential term here tries to twist the distribution and to make it very concentrated on the rare event region, which is close to 0. This is the region where we are interested, in. And that's why for this particular case, theta star should go to minus infinity as the event is rare and rare. Okay. But this exponential twisting has some restrictive drawbacks. First, sampling according to the exponential twisting univariate PDF is not straightforward. So people use some acceptance rejection, and if it's not done efficiently, this can lead to a high computational cost per sample. Another problem is that, which is also restrictive, that this method needs the knowledge of the moment generating function, which is not the case for the log normal distribution, especially when theta is positive, the m of theta is infinity. So for heavy tail distribution, this is not finite even. And also the theta star, we should do some, solve it numerically because we don't have a closed form expression. So what we aim to do then, we try to provide a very simple change of measure that for certain class of distribution that we will talk about later, we get the same performance of the exponential twisting, which is the best in some sense, without introducing these limitations. How we do this? So we first consider the class of distribution that they behave like a polynomial around 0. So they can be written as x to the power p times some g of x, where g of x is just asymptotically constant around 0. And then actually this class of distribution include a lot of very known distributions that are commonly used in communication systems. And the idea is as follows. So since as I told you, the exponential twisting is trying to shift the distribution around 0. And since the behavior of the distribution around 0 is almost x to the power p, so what we propose as twisting is the same as the exponential twisting one by removing only g, which behave like a constant. We don't need it in the red event regime. And suddenly, this is very simple gamma distribution. But we know how to sample from, and we know also how to solve this nonlinear equation because we know m of theta explicitly, and then we get the shape parameter, which is p by assumption, and theta tilde is the one that is given by 7. So what is the result of this? For this class of distribution, we show that in the regime of interest, we have the same performance as the exponential twisting without introducing any limitation. We know how to sample, we know how to compute explicitly this twisting parameter. Now we move to another class, which is much more difficult. These are distributions that do not approach the 0 polynomially. So it's very, very difficult to handle this kind of distributions, and we have to tackle this problem in a case-by-case basis. So we consider particularly the sum of IID log normals, whose PDF decreases to 0 at a faster rate than any polynomials. And this is the source of the problem, that we cannot use any Taylor. The Taylor expansion around 0 of the log normal distribution does not exist. So note that this problem has been tackled before using this exponential twisting that I described to you, but by first providing an unbiased estimator of the moment generating function, because we don't know MGF. They approximate theta by some numerical method, and they use acceptance rejection to sample from the important sampling PDF. And we'll see later that this will generate some additional cost per sample. So in the case of the log normal, we derived two estimators. The first is a biased estimator, and the idea is quite simple. So we start with the quantity of interest, and we just apply the law of total probability, and we just keep the first term, the law of total probability, which is the one where we condition over the fact that xi is larger than delta gamma over n, where delta is chosen parameter between 0 and 1. So next to just, we know that, we know the CDF of a log normal, so this is known, and we will just play with this, try to estimate this quantity here. So for simplicity, we consider f bar to be the PDF of the truncation over this set here, and we write this quantity here as the left tail probability of xi, which are just the truncation with respect to this PDF here. So what is the motivation of doing this actually? So now, since we don't have Taylor expansion around 0, we try to truncate the space. Somehow, we now know how to do, we have a Taylor expansion around this point here. So the idea is just to do Taylor expansion now. So I recall here the exponential twisting when applied to this probability, it is just the original one, the original PDF, times this exponential of theta x. And then we just use Taylor expansion of this function f bar here around this point. So by doing so, we get this formula here. So it's very easy to understand. And then the approximate exponential twisting that we propose is just we take the first two terms in the expansion, and this is how we will use important sampling. The normalizer constant is very easy, just given by just integrating this quantity here, and the theta, the best theta within this family is given by this formula, and it is just given by solving this nonlinear equation. Now the last question is how to sample from this PDF that is here. So the idea is simple. We just write it as a linear, as a combination of two PDF, and then we just use a coin to decide from which we sample, depending on the output of the coin. Now, what is missing is how to choose this delta. For this, we just start with the global relative error, and we split it into two errors. One is the bias, and the other, the relative bias, and the other is a relative statistical error. So for the relative statistical error, it's used to control the number of samples, and we try to choose delta such that this term here is bounded by epsilon over 2. And if we control the statistical error by epsilon over 2, then we control the global error by epsilon. And here we get a possible choice to find delta as a function of the tolerance, n and gamma, which is given by this formula here, where phi is the CDF of the standard normal distribution. And this formula here ensures that the relative bias is bounded by epsilon over 2. So now we move to the second estimator in this framework. So we observed numerically that when we have a small value of delta, this biased estimator behaves like a gamma distribution with shape parameter equal to 2. So it means that if we go back, yeah, this important sampling that we propose, it is only this term that is dominating, and this term it's a shifted gamma distribution with shape parameter equal to 2. Then so the idea is just to use a gamma family again in this log normal case, and we try to optimize the shape parameter. So I recall here the gamma PDF. Again, the value of theta is chosen as follows. So to ensure that the expected value of each of the random variable with respect to this new PDF is gamma over n, and hence the expected value of the sum is gamma. So we make sure that we don't have problem with error event. And then for the choice of k, we first try the likelihood ratio, then we bound it, and we simplify it using the Stirling's formula. And the idea is to choose k to be the minimizer of this upper bound. So what we get this formula, which is function of log of n over gamma. So it makes sense. So when we increase n, the k should increase, and when we decrease gamma, also k increases with the rate of with the logarithmic rate. Okay, let us show some numerical results. We start with the viable case, and we plot here the squared coefficient of variation as a function of n. This is our method, and this is another very known method, which is what we call the hazard rate twisting technique. We'll come back to this later. So we see from these two plots that we have reduced the variance, and from this point here, the reduction is of a factor of more than 250. Here we fixed the two values of n, so n equal to 8 and n equal to 10. So this is a type which should be n. And we plot the squared coefficient of variation as a function of the threshold. And interestingly, we see that for our method, increasing n does not affect too much the efficiency of the estimator. However, by going from 8 to 10 in this method here, we make the variance very, very well. I mean, we worsen the variance. We go to the log normal case, and here we make the comparison with the work of Asmussen and co-authors, and we plot the squared coefficient of variation as a function of n. This is the one given by the exponential twisting, and this is the two proposed approach. So for the log normal case, we don't, the aim is to retrieve the efficiency of the exponential twisting, but for this case, we did better actually than the exponential twisting, as you see here. And we get a reduction of order 30. Again, if we plot the squared coefficient of variation as a function of gamma, for two values of n, we would get the same conclusion, that if increasing n does not have too much effect on the proposed approach compared to the others. So the comparison before was made in terms of variance, but now we want to include the computing time in our comparison, and we define what we call the work normalized relative variance, which is defined as the squared coefficient of variation over the number of samples times the computing time in seconds, and the computing time is the time needed to get an estimator of using MIAD samples of estimator here. So how to understand this work normalized relative error variance? So if we compare to estimator, the one that exhibits less work normalized relative other, because it achieves less error for a given computational budget, or equivalently, it needs less computing time to achieve a fixed relative error. So if we do the comparison in terms of work normalized relative variance, we see that our two approaches are much more efficient than the exponential twisting technique. And interestingly, the reduction in terms of number of samples worth 30, but now the reduction in terms of work normalized relative variance is multiplied by 10. This means that in addition to reducing the variance, we reduce the computing time as well. And this is related to the fact that the exponential twisting has this limitation of using acceptance rejection and so forth. Okay, so I will just summarize part one before I go to part two. So we developed an efficient importance sampling estimator to estimate rare event probabilities corresponding to the left tail of the CDF of large sums of non-negative IID random variables. We achieved for two classes of distribution at least the same performance of the well-known exponential twisting. And we validated numerically the efficiency in the event of in the regime of interest corresponding to large n and small gamma. So as a future direction, we may think of providing some theoretical study of the variance with respect to n and gamma. And for more details, I just give you here the paper from where, so you can get more details about this approach. So before I go to part two, I would like to ask you if you have any question. Yeah. Okay. Then I go to part two. So in this part, we consider again X to be a random vector composed of independent positive components. Actually, positivity is not needed here, but we just, it's motivated from the applications. That's it. So we can just erase this assumption here. And then let us denote by Sn to be the partial sum of Xi, and G to be a function from R plus to R. It's an arbitrary function. And what we aim to do here is we aim to estimate rare event quantities that could be written in the form of an expectation of G applied to S at the final step N. And more precisely, we will try to develop a state-dependent importance sampling algorithm. And by state-dependent algorithm, we mean that the parameter of the importance sampling are chosen in a dynamic fashion, in the sense that the parameter of the importance sampling in a given step depends on the current step and the current state of the system. And we will see that how we will connect importance sampling to stochastic optimal control to find this importance sampling parameter or to find this control. So the applications are again mainly motivated from communication systems. The first one is the one that I presented in part one. It's related to the outage probability at the output of some diversity receivers. And in this case, G is just the indicator function of X being less than given threshold. Another interesting application that can be written in this form here is to evaluate again the outage probability, but in the presence of some interference. So, to just to motivate this, we consider again the transmitter and the receiver that are communicating, and this is the desired user power. And we assume that there are interfering signals that are there are other users that communicate with the same receiver using the same frequency. And then in this framework, it's important to introduce the signal to interference plus noise ratio, which is given by the ratio between the signal, the desired signal power, over the sum of the interference plus the eta here, which is the variance of the additive white Gaussian noise. First, here it's important to assume that the interference are these random variables here. All the random variables are independent. And how to make this expression in the form of an expectation of some sums of random variable. The idea is just simple. We condition over x1 to xn and do the law of total expectation to write the same probability as here. And we see that this can be written as the form of some expectation of sums of functions of a function of sums of random variables. This simple expression or the simple idea can be obtained for a more complicated wireless system like multiple input, multiple output systems. Also, we can have the same probability for discrete random variables, and this is related to free space optical communication systems, and the probability of missed detection is the sum, probability of the weighted sum of Poisson random variables being less than the threshold. Again, this is the same. We can put it as in the form of 14. So let us discuss a little bit the literature. So the literature is very rich of variance reduction techniques that deal with the right tail and the left tail of sums of independent random variables. This is, I mean, very big field. And in particular, there are a lot of work that they use state-independent importance sampling techniques. And by state-independent, the parameter of the importance sampling are just constants, do not depend on the state of the dynamics of the dynamics. However, in this paper, they have shown that for certain rare event that involve heavy-tailed random variables, state-independent change of measure are not efficient. And this has led researchers to consider more complex state-dependent importance sampling techniques. And here I will just talk briefly about the two of them, which are the most, which are very close to what we are doing. So in this paper, for instance, they consider very particular heavy-tailed distribution, and they consider a family of change of measure. And this, the parameter of this family are determined via solving a deterministic discrete control problem. But this one is the one that is very close to what we are doing. So it makes the connection between importance sampling and optimal control, but it works only for IAD case and for distribution that have finite homogeneous functions. So let us now talk about how to connect importance sampling to stochastic optimal control. So the idea is very simple. So we try to embed the static problem with the evolution of Markov chain. So we start with S0 equal to 0, and then Sn plus 1 is just Sn plus Xn plus 1. And then instead of sampling Xn plus 1 from its original distribution, we perform a change of measure such that given Sn, Xn plus 1 is distributed according to this new probability density function that depends on mu, which is function of the current step and also of the current state. So using this idea, we can write the new importance sampling joint PDF as the product of the conditional PDF, as here. And the aim is to find the optimal control, mu n, in some admissible set, such that the second moment of the importance sampling estimator is minimized. So for this, we define the cost function corresponding to this stochastic optimal control problem. So the cost function is just the second moment of our importance sampling estimator. So it is just G multiplied by the likelihood ratio, G squared multiplied by the likelihood ratio squared, given that Sn at step n is equal to S. A calligraphic here is just the set of admissible Markov controls. It is important to make to mention here that compared to standard optimal control problem, we have a multiplicative cost structure. So it's a final cost times some random cost. However, in standard optimal control problem, we have additive structure. So we define also the value function to be the infimum over all possible admissible controls of the second moment of the estimator, which is here. So then we prove a dynamic programming equation. So the value function satisfies this equation in 21, which is solved by going backward in time. And the final condition is that u at the final step and x is equal to g of x squared. And if the minimum of the infimum is attained, then we get the control to be the argmean of this quantity here. So Sn plus 1 that is appearing here is just equal to S plus Xn plus 1, where Xn plus 1 is distributed according to this new probability density function. Of course, parameterized by mu. Now, up to now, we didn't talk about the choice of the parameterized family of probability density functions. And for this work, we choose to work with the hazard rate twisting technique, which was originally developed to deal with the right tail of sums of heavy-tailed random variables, and then it has been extended to some to more general cases. So what is the idea of this hazard rate twisting? We first define the hazard rate to be the ratio between the PDF and the complementary CDF of, this is associated to the random variable xi, of course. And then we define the hazard function to be minus log of 1 minus the CDF. So the derivative of this hazard function, it is just the hazard rate. Then we can write actually the PDF of xi using the hazard rate and hazard function as follows. And the hazard rate change of measure is obtained by twisting the hazard rate of each component xi by quantity mu I that should belong to minus infinity to 1 to ensure that this new PDF integrates to 1. So when we take mu to be 0, then we go back to the original measure. Okay. Now let us discuss how we solve this dynamic programming numerically. So first we truncate the state space R plus and work on this interval for S to be sufficiently large in R plus. It is important that for some cases we don't need to truncate and S is chosen naturally. So this is the case where we have this left tail probability. And since we know that the value function is 0 after, for S that are larger than gamma, then we just choose S to be the threshold. In general, we do some linear extrapolation to compute the value function for S that are larger than capital S. Also, we discretize this the interval 0S to using this mesh here. And the first step of the algorithm is to use the fact that the final value function is G, and then we go one step and solve for UN minus 1. And this is not computationally demanding because it is just one D integral to be solved. And the control is just solved by numerically solving this equation 28. Now we go another one step. After computing UN minus 1, we go and compute UN minus 2. But here we need to do some linear interpolation because in the previous step, we have computed mu n minus 1 only on the grid points. And of course, if needed, we use some linear extrapolation as well. And we repeat step 2 up to reaching U0S, the quantity of interest. Now, after doing this backward step, we go and solve the backward of the forward step. So what is the forward step? We start with S0 to be 0, and then we sample from this PDF that is parameterized by mu1. And mu1 is just, it was computed from the backward step. Now, after this, we will get S1. Since the control had been only computed in the grid, and to avoid that the case where the control are not smooth, we need to, in the forward step, we need to solve again the minimization problem in order to get the control. This step, as we will see later, can be avoided if we have a smooth control. Then we can interpolate between the grid points. So after computing mu2, we take one step and go forward to the next step. where x2 is sampled from this control that we just found. Now we keep repeating this until we get mu n, and also the final step is to sample from x. We repeat this step 3 m times, and our importance sampling estimator is given by this formula here. Just I want to go back to the to this step here. As I said, if we have a smooth control, we can avoid doing this minimization problem by just doing interpolation between the points. And this is clear numerically for this simple left tail problem in the standard log normal case. We see that the optimal control are smooth enough, and it makes sense to do linear interpolation between the points. Now let us discuss let us make some remarks about the cost. So if we denote by HRT, stochastic optimal control, to be our estimator, and this one is the same, I mean, it's the one that is developed here, but without doing optimal control. So the control are state independent. There is no, they're constant. So let us denote this quantity to be the number of required simulation runs to ensure a relative error equal to total. Then our work is basically composed of two costs: the backward cost to get the control, and the forward cost, which is the cost of Monte Carlo. But without doing any optimal control, the cost of this method is just given by the forward cost. So interestingly, when we are in the regime of rare events, I mean, when the event is very rare, so this cost will dominate both of them, and then the backward cost would be just negligible compared to this cost. But for moderate value of the probability, this cost can be large, and we need to do something in order to reduce this backward cost. So what's the idea? The idea is to divide the sum Sn into B blocks and compute the control for each block rather than for each xi. This, of course, will reduce the backward cost from n times k times this constant tb to b times k times tb. And we call this method the aggregate method. So mathematically, we choose b to be in this set from 1 to n. So when b is equal to n, we go back to the previous case. And when b is equal to 1, we have the hazard rate twisting without any control. So it's deterministic. It's a constant. The control are constants. So we choose b here, and we consider this reformulated somehow dynamics. So the state after m plus 1 blocks is the state after the mth block plus the sum of this xi. So this xi that belong to the same block are treated similarly in terms of variance, in terms of change of measure. So what I mean that we use the same control for all the xi that are in this block here, and the control is just function of this term of this SNM. So of course, how we can get easily if we solve this B optimal control, we can get easily the original control through this formula here. It is really important to understand here that we decrease the cost of the backward step with the price, of course, of increasing the variance. So, and the aim is to somehow to make sure that the cost, that the amount of reduction in the cost should be more than the amount of, should not worsen the variance too much in order for the method to work. So how to get this B control? So if we follow the same proof as in the dynamic programming, we will get this relationship between UM and UM plus 1. And since we keep the same control for all the xi that are in the same and the nth block, we will just need to integrate Bm, an integral of size, in dimension Bm. Of course, we will not do this in practice, and instead we will approximate this quantity here by some expression that involves one-dimensional integral. And there are tricks to do this. All the tricks are to play with respect to this sum of the hazard functions here. Okay, so let us discuss the numerics of this part. So first we consider this left tape problem again. So the comparison is done with respect to the hazard rate twisting technique, without where the control are fixed and are state independent, and also to the same exponential twisting estimator of Asmussen and his co-authors. Now, for the aggregate method, we use this inequality that holds asymptotically when this term in the sum inside the hazard function is sufficiently small, which is the case in our case. So if we use this inequality in the previous dynamic programming equation, we just get rid of this high dimensional integral, but we need to have to know the PDF of sums of log normal random variables, which is also a difficult problem. So what we did, since we do this for just roughly, because we don't need to solve the control exactly, then we approximate the sum of log normal by one log normal, and we do moment matching. Okay, so the first result. So the green one is the hazard rate twisting with the stochastic optimal control, and it gives the best result out of all the compared to the hazard rate twisting technique and to the exponential twisting technique. We observed also that this aggregate method that we introduced worsened the variance as expected. Also, for the efficiency, we reduced the variance by a factor of more than 41,000 compared to the hazard rate twisting technique, which does not use any optimal control. So this is the gain from the green to the yellow one, because they are basically the same method, one without stochastic optimal control and one with the stochastic optimal control. And you see the gain of using this state-dependent important sampling scheme. So in terms of CPU time, we see that even if the aggregate method requires more samples than the stochastic optimal control one, the CPU time for the aggregate method is less than the one of the green curve here. So it means that the aggregate method, even if the reduction is not too much, but it works well as we expect. So the reduction in the cost is much more important than the increase of the variance. Here, just to mention that we plot here for these two green plot. One is for the backward cost and one for the forward cost. Just to mention that the cost is basically due to the backward step here, not to the forward step. We do the same as a function of n now, not as a function of gamma. So I forget to mention that here we are not optimizing over the block size B. We choose it to be 2 for simplicity, but if we optimize it, we will find a curve that maybe behave like this. So now we do the same as the function of n. So for the block size, we choose it to be 2 when n is even, and when n is odd, we choose it to be equal to 2, unless the last step we choose the block to be 3. So we see, we get the same conclusions. So we have we get a substantial amount of variance reduction with respect to this hazard rate twisting technique. And again, we see that the aggregate method reduces the cost, the backward cost of the method, of the original one, up to some value of n, but then it gets worse. What happened here? So here the backward cost becomes negligible compared to the forward cost, and it is more important to optimize m to minimize the variance instead of reducing the cost of the backward step. This is what I just said now. So for small threshold and large n, so in the regime of rare event, so we observe that constant block B is less efficient in terms of CPU time than the green one, and this is again due to the fact that the backward cost is negligible in this case. Generally, this block size has to be chosen in an adaptive way. So we try to minimize the total cost with respect to the size block M and the K the size of the mesh, subject to this various cost rate. And what is challenging here that one should get a good estimate of the variance of the estimator with respect to B and K in this case. But in some regions, we know how to choose this block sizes. So in the regime of rare events, as I said, it's not important to optimize the backward cost. So in this case, we don't need to choose the capital B to Bn. So we don't do any aggregate method. But before, we choose B to B1 to count all the random variables to be in a single block, because in this case, as we see here, the hazard rate twisting is much more better than what we are doing. So this should be done in an adaptive way in order to get good results. So this is summarized here actually. So this is what I. Now we move to the second application, which is related to the outage probability in the presence of co-channel interferences. So this is the expression of the outage probability, and here I just wanted to motivate the use of importance sampling. So if we plot the original PDF of the sum, and also plot the function G here, which is the CDF of X0, we see that when we sample from the blue one, most of the sample are not important. They belong to the non-important set. So we need to do important sampling by shifting this blue curve. So this here I just plot the optimal density, which is just the product between the, which is proportional to the product between the blue one and the red one. And we see that we need to make some shift in order to get good result, good variance reduction. So the comparison is made with respect to this covariance matrix scaling technique here, and also to exponential twisting that is done by Zdravko and Pierre Lecoyer. So for the aggregate method, we use this inequality again in order to avoid this high dimensional integral. And we get this approximate dynamic programming equation that is solved by U here, which needs only one dimensional integration and simple minimization problem. So for the result, something very important happened here. So the aggregate method does not worsen the variance. So even if we don't do this optimally, there is no effect on the variance. This means that we reduce the cost without worsening the variance, which is very important. And this is clear. So the green and the black one coincides in this simulation. So just to give some numbers, so we get a reduction of 2,000, factor of 2,000 compared to this approach based on scaling the covariance matrix of the multivariate Gaussian here in this case. So this is also very important result, which is related to the previous observation. So the aggregate method just reduces the cost, and it behaves very, very well compared to the one that tries to optimize to get the minimum variance. So it's very, in this case here, it's very important to use the aggregate method because we decrease the cost without making the variance larger. Again, this is done only for B equal to 2, which is not optimized. So one can think of optimizing B and get maybe a result, like very small result, very small variance. We do the same. So we plot the number of samples and the CPU time as a function of the tolerance, of the relative tolerance, and we get the same observation, right? So we get the same result using the stochastic optimal control approach and also the aggregate method. And we using this aggregate method, non-optimized still, we get a nice reduction of the cost. So let me make a summary. So we developed a generic state-dependent importance sampling algorithm in order to efficiently estimate rare event quantities that could be written in a form of an expectation of some functions of sums of independence. So all the discussion should be under the constraint of independence. So we choose the hazard rate twisting technique family of change of measure, and we connect our problem to optimal control to find the twisting parameter, and we observe numerically that we reduce the variance compared to some very known estimators. We also proposed an aggregate method to further improve the cost of the backward step. as a future direction, we try to optimize the aggregate method and to choose the block sizes optimally, and also to extend this approach to the multivariate case. And in this case, we will not solve numerically the backward step. Maybe we use some machine learning techniques to approximate the value function. And for further details, I just mentioned here the paper that is recently submitted. And that's it. I mean, this is the references, and thank you very much.
Thank you for your talk. Do we have questions from the audience?
I have a question.
Hang on, let me give you.
Thank you, Nadhir, for the very nice presentation. I don't know if you mentioned how you were performing the stochastic optimal control.
Okay.
The stochastic optimal control that you're performing to get your importance sampling. I didn't get how you were performing it.
Okay, so what we would like actually to compute is some expectation of some functions of S at the final time n.
Yes.
So what we did, so we write this Markov, we just write this Markov chain, and then to instead of originally we know how to sample xn, all the xn, they're independent, so they have the same distribution. But instead of doing this, in order to go to the importance region, we choose to, instead of sampling from the original one, we sample from the new density that is here. So in our case, we choose it to be the hazard rate twisting PDF. But instead of what is important here, that the density is parameterized by this control here. So depending on your path, somehow, if you want to talk about path here, you choose this control. If you are far from the region of interest, you try to push your path to the region of interest. If you are if by luck you are close to the region of interest, you don't use the control. You just take mu equal to 0.
So here you don't actually need to solve an optimization problem.
Again?
You don't actually need to solve an optimization problem.
I mean, we solved an optimization problem, but maybe I didn't have the time to talk about it. It's here. So we approximate this integral by using some quadrature, and then we use some numerical method to solve this control here.
So you can use the structure of your problem to approximate your solution.
Yes, of course. I mean, we have to use something from the problem. But what is important here that we this dynamic programming. So we start with d square, which is coming from the quantity of interest, and then we link the best value function in two consecutive steps. So we are using actually the dynamic or the characteristic of the original problem to find the best control. Of course, it's not a black box.
Okay, I see. So here your small s is arbitrary. That's what you said.
Yeah, this is for all s.
Okay.
Yeah.
Thank you very much.
Thank you. Thank you.
If any further questions for the speaker?
Just, I'm curious. So the first approach was solving a similar example. I mean, one of the applications that the second approach was solving, and you showed that it's better than the Amazon approach in some sense. Did you compare, I mean, also to that approach?
Yeah, this is a very nice question. So direct consequence of these two approaches to combine them, because we showed in the first part the gamma family is performing very well. So we didn't do the first part because the gamma family has two parameters, and the optimization is not easy. So we choose the hazard rate twisting because of the structure. I mean, they are easy to use and to optimize and everything. But as a future extension, we have to use the family that we found in the first part and put it in the optimal control problem and get better result for sure. But this is very nice. Thank you.
Thank you. Do we have any more questions? Actually, I have a couple of questions for a change. So if we get a look at equation 31, please.
Equation 31.
Yeah, can you say something about the variance of this importance weight, the product as n gets large? Because it looks a bit worrying to me.
So the variance of the likelihood, right? So this is the likelihood.
Yeah. So this importance weight, yeah, as a function of n.
But this is the. I mean, we are solving the optimal control problem. I mean, so by trying to minimize this variance. So if we solve the optimal control problem correctly, then the variance is controlled within this family of distribution.
Are you saying is order 1 with respect? Is it order 1 with respect to n? Because that would be very surprising to me.
With respect to what?
Capital N.
Yeah, how to say? So the idea is that for a given n. So if we have fixed n here.
Yeah.
And then we try to find, if we consider the family, we try to find the best change of measure for that given n. How it behaves with respect to n, this is another story.
Yeah. That was my question really, because
this is related to shape question. So in the first approach, we said that the gamma distribution solves this large n problem. So I think when we choose the gamma family in this case, and try to use the optimal control problem, we will get a nice problem.
Okay, I mean, because normally these things order exponential in n, so that's why I asked. And so that comes to my second question, which is you can rewrite this problem as basically a problem of estimating sequences of normalizing constants, which give you essentially the estimator of the rare event probability, and then you would have a product of sums which are numerically stable, which is basically adaptive multi-level splitting. If you looked at that, how does that work for these problems?
Actually, I worked on this splitting. The problem with splitting is there is not too much theoretical. So it's very nice approach because it's based on the subset approximation, but it shows very good numerical results, but there are missing a lot of theory. I think that's why we try to connect to optimal control. But yeah, you are right. I think one can also try to compare this to splitting and see what kind of result we get. But it's a very nice question.
Thanks. Yeah, there's some work by Gallardo and Seru, which might be relevant here. But yeah, thanks. Do we have any more questions? If not, thanks, speaker. Thank you very much for your talk. Thank you.
Stop sharing.
Let's